So now we will have our next event, which is live Q&A session. So we have with us Professor Andrew Eckford. So let me first bring them on the stage. So this session will be chaired by Professor Swami from IIT Kanpur. His research interests are in wireless networks, machine learning, and I request Professor Swami to chair this session.
Good evening, Professor Andrew.
Hello, how are you?
I hope you have got the questions given by the audience. Did you get a copy of it? Yeah.
Yes, I'm sharing my screen right now.
Sure. We are able to see the questions. So, while Professor Andrew answers these questions, if there are any other questions, you can type in the Q&A. I'll hand over to Professor Andrew to continue the question.
Thank you. This is now day 3, and I hope you're enjoying the lectures. Professor Banerjee passed me some extra questions from the last series of lectures, lecture 7, although I do think we answered these questions live yesterday. Nonetheless, I'll just go through them for complete clarity. I see some technical difficulties with the non-absorbing model. Brownian motion will be in and out of the receiver boundary infinitely often in a very short period. The problem is associated with Brownian local times. How is this handled in the receiver model? Do we tag molecules and keep track of them? If yes, is there some way to do it in practice? We addressed this question yesterday. So the problem of molecules going in and out of the receiver volume is difficult to handle mathematically. What we normally do in analysis is we simply make something like a Gaussian assumption so that we're not required, which does 2 things. One is it doesn't require us to keep track of the locations of individual molecules, which is difficult. And secondly, it allows us only to deal with the cross correlation between times. Now you'll notice in my lectures, we do deal with this point, and but we don't deal with time correlation. We only deal with it at individual times. So that is an issue that has to be dealt with, and it has to be dealt with carefully in the model. So this part of the question was interesting. We actually talked about this yesterday as well. Do we tag molecules and keep track of them? So it turns out that if you tag a molecule at the boundary, then if you tag it in such a way that you realize you've seen it before, then the model actually reduces to the absorbing model. And the reason is because if you tag a molecule with the fact that you've already seen it at the boundary and you know what time you saw it at the boundary, then you have all the information you need about its Brownian motion from the past. And continuing to observe that molecule gives you no new information due to the Markov property. Second question, how about out of order delivery? We also talked about this a little bit last time. So out of order delivery of molecules, basically what you have, let's suppose you transmit a molecule at time 0 and a molecule at time 1 second. Suppose they are indistinguishable due to their random motions. They might arrive in the same order that they were released, or they might arrive in the opposite order. So you can imagine that this would get even more complicated the more molecules you release. There is a result from a pair of Indian mathematicians from about 30 years ago. Their names were Bapat and Beg. And what they said was that in order to simply write down the probability density function, taking into account the out of order delivery, basically there's no alternative except to sum over all of the possible permutations. And this actually belongs to a complexity class that is worse than NP complete.
Andrew, I have a follow-up question. You in the last Q&A, you mentioned about work of a group of researchers who are trying to address this non-absorbing receivers. I missed that part.
Right. So there are some groups who work on that. I tend to work on absorbing receivers because they're mathematically more tractable. I can provide you with some links later
okay.
so that you can see
okay.
some papers.
Okay.
I don't have any right off the top of my head, but I'll follow up with you later.
Okay. Thanks.
Okay, moving on to lecture 9. And again, I'm very happy to be interrupted at any time to follow up or to discuss more. Moving on to lecture 9, is multiplexing possible at the transmitter end in molecular communication like we do in wireless communication? Absolutely. There's no reason why you can't use any particular technique that works in wireless communication. There's no reason why you can't use it in molecular communication, at least in the baseband. So there are challenges, of course. There's, as we've talked about, there are heavy tails to the impulse response. So there's a lot of ISI. So as long as you do something to take the ISI into account, then you can do whatever you like. So multiplexing is certainly possible, and you could easily imagine how this might be done. So you could do time division, for instance. You could have a certain concentration for a certain time, then maybe a guard time, and then maybe someone else's transmission in a different time slot. So you can do time division, for example. And if you think about it, you can think about the ways in which all the other forms of multiplexing could also be used. Among these 3 modulation schemes, what is the most convenient to use in MC? I would say that concentration shift keying is the one that's seen the most. So both in terms of the lab implementations that I've seen, as well as natural communication systems, they tend to revolve around concentration shift keying. As far as using different molecules, sometimes we call that molecule shift keying. That's very conceptually simple, and it's sort of easy to understand that you send a 0 with one type of molecule, a 1 with another type. So that's conceptually simple. The third type of timing, I actually like to think that timing subsumes all of the other kinds. So if you can specify exactly when you release every molecule, then that actually includes concentration shift keying. So in concentration, you simply decide to release a lot of molecules all at once, but nonetheless, you can specify the times of release of all the molecules. Can we use any pre-coding techniques at the receiver as we don't have channel information at the transmitter end? Okay, this is an interesting question. I'm trying to think if I've ever seen that done, and I can't think of any papers off the top of my head. But as I said in response to question 1, there's no reason why you can't. If the channel is linear, and it normally is in terms of concentration shift keying, there's no reason why you can't use linear techniques like linear pre-coding. There's a couple of complications, of course. One is that the channel is non-negative, so you actually can't transmit a negative signal. That problem can be overcome by basically transmitting a bias. So the same problem actually arises in optical communication, where it's similarly non-negative. And I have a colleague at a university close to mine named Steve Hranulovich, and he's done a lot of interesting work on optical channels where you can't transmit negative signals, but nonetheless you can basically have nice linear combinations like we're used to in standard communication. So what I also wanted to say is I'm not sure if this has been done. I can't think of any papers off the top of my head. But if you told me that there was a paper, I wouldn't be surprised. Someone might be trying it right now. In molecular shift keying, we use different types of molecules for sending different symbols. Such a system may require many reservoirs and efficient molecule release mechanisms. How are such issues addressed in the literature, considering the limited functionality of nanomachines? How are they addressed? I would say they are addressed the way we normally address these problems in theory, which is that we just make an assumption that it's possible. So I don't think anyone has thought very deeply about how complicated this might be, and you're absolutely right, it is very complicated. Moreover, one reason, and I think I mentioned this in my lecture, while molecular shift keying is conceptually very simple, if you have more than one distinguishable type of molecule, you can actually do better. So basically that's like having 2 different frequencies. So in wireless communication, you could send a signal as follows. If it's a 0, you send it at frequency f1. And if it's a 1, or excuse me, you send it at frequency f0. If it's a 1, you send it at frequency f1. So I mean, excuse me, you can do frequency shift keying. Nobody does this because it's inefficient. If you have 2 frequencies, it's generally more efficient to code independently on both. So generally speaking, we don't see this very much. Lecture 10, First question, in TA equals TR plus Z, how is Z assumed to be Gaussian? So I assume you are referring to this, where the arrival time, so I brought up lecture 10 here, where the arrival time is equal to the reception time plus the first arrival time, where we treat the first arrival time as Gaussian noise. So in fact, it is not Gaussian. So we talked about a couple possible distributions for the noise, but I do understand the confusion. So here, I gave an example of what might happen if it was Gaussian, which is something that we are familiar with in conventional communication systems. So this was only intended to be an example. The noise is not Gaussian. So we talked about a couple of distributions you could have. If there's no drift between the transmitter and receiver, you have the Levy distribution. And if there is drift from the transmitter to receiver, you have the inverse Gaussian distribution. And so this was just intended to be an example to recall how these problems are solved when we have a conventional communication system, and you could adapt this solution to, for example, the Levy distribution, which I do down here.
See an additive effect, or is it like some other multiplicative effects also on the received signal, or is just?
So that depends on how you assume that the receiver works. So in the mathematical models that we present, often we just assume that the receiver simply measures the time of arrival, or can count the number of arrivals. In that case, so for time of arrival, it's not really linear, but it's also not really multiplicative. For concentration, the average value is additive, the average value is linear, but it turns out that, I think I pointed this out in some lecture, I don't remember which one, the variance of the count is actually dependent on the mean. So right. In other words, the more molecules you have, the more variance.
Yeah, it was there in today's lecture, one of the lectures. Yeah.
Right.
Thanks.
Sir, you are considering one dimension for timing modulation, but the Brownian motion is a three-dimensional process. So is there a correlation between them, or are these independent scenarios? Moreover, sir, where one dimension timing modulation would be used in practical scenarios? Okay, excellent questions. So we use one dimension because it's analytically simple. Because I only have 8 hours, I can't go into a lot of very technical details. But another issue is that the three dimensions of the Brownian motion are assumed to be independent. So there might be some dependence I'm trying to think of a scenario in which there would be dependence amongst the various directions. It's possible you'd have dependence if you allowed viscous friction. I know that there's time dependence in viscous friction, but I don't know about, I'm not sure if that would make the three dimensions of the motion correlated. I don't think so, now that I think about it a little bit. This question, though, is interesting. Moreover, sir, where one dimension timing modulation would be used in practical scenarios. So I think I explained this in one of the lectures, that if you imagine that the transmitter is at the origin, and the receiver is an infinite plane located where the closest point on that infinite plane is distance d away. Because the three dimensions of the Brownian motion are independent, it's only the distance to the plane that matters. So it's only that one dimension that matters, and it reduces to the one-dimensional case. You might remember, if you've taken a course in electromagnetism, a similar kind of model is used when you are very close to a sphere. So if you're very close to a sphere, it turns out the field is well described by an infinite plane. So the same scenario would occur here. So if you're very, very close to the surface, if you imagine a cell as a sphere and your transmitter is very close to the surface of that cell, you assume that it's very close to the surface of the cell. In other words, much closer than the dimension of the cell. Then from the transmitter's perspective, it would look like an infinite plane. So that might be a way in which to model it. What if we send unique signaling molecule every time from the transmitter to avoid the arrangement problems? Okay, that's a great solution. The problem comes back to up here, this question. which is that it's actually complicated to keep those around. It's complicated. I mean, you could do one of two things. You could either manufacture molecules with an individual serial number or something, so that you could make sure that you know what order they were transmitted in. That's complicated. You could do something like DNA synthesis at the transmitter, but that would be difficult to control. And also, as I mentioned, it turns out that if you have multiple distinguishable molecules, you can treat them as independent channels. So in fact, this method, while conceptually easy to understand, probably also relatively, probably easy to develop a communication system, if not to implement the many reservoirs or synthesis systems that you would need. It would be relatively simple to implement, but there are more efficient ways to do it. And in fact, we don't see this very much in nature. Avoids this. Nature doesn't tend to send distinct molecules, so that's kind of an interesting indication that it's either difficult or inefficient. Okay, in molecular communication channels, the received number of molecules is often approximated to Gaussian as well as Poisson distributed. Considering the smaller arrival probability and the low number of transmitted molecules due to the limited capacity of nanomachines, isn't the Poisson approximation better than Gaussian? Of course, so depending on what the parameters of the system are, the distance between transmitter and receiver, the number of molecules released, the diffusion coefficient of the channel, yes, it might be possible that the average number of received molecules is very small, in which case the Poisson approximation would be better than the Gaussian. Now, we don't talk a lot about the Poisson distribution in this course. Again, I only had 8 hours, so but this is an excellent point, that if there's a small number of arrivals, then Poisson would be a better model. How should we set the sampling time? Means if we have any optimum value of TS. So in other words, I suppose this is the time between symbols. That is actually not a terribly, there's no simple answer to that. So if you have short TS, then you transmit lots of bits, but ISI is very bad. If you have long TS, then ISI isn't so bad, but you don't transmit very many bits. So the answer is complicated. So people do write whole papers about the optimum symbol time, and it tends to depend on the scenario that you're considering. I've seen a lot of interesting papers recently about optimal decision times for mobile molecular communication when the distance between the transmitter and receiver is changing, in which case presumably the optimal value of the symbol time would also change. So not a terribly, it's a really good question, and I would call this kind of an open problem. I mean, you could pose the problem, you could set it up mathematically, you could ask what the optimum is and solve it, but there's no general answer is what I'm getting at. Lecture 12, can we use the techniques of wireless communication to mitigate ISI and MC, like adding cyclic prefix and OFDM?
Andrew, there's a continuing question of question number 3 of lecture 10.
Sorry, I apologize. I haven't been checking.
It's in Q&A.
I've been checking the Q&A over here. Okay, yes, from Gaurav Sharma. Does Gaurav want to ask his question in person?
Okay, sure. Let me just bring him. Gaurav, you can switch on your mic and camera, and you can directly ask. Yes.
Perhaps I can just read the question out loud. Sir, in continuation to the question 3 of lecture 10, if we have 2 absorbing receivers in the 1D plane, is there a scenario where they would behave mutually independent of one another? Okay, if you have a 1D plane with 2 absorbing receivers, then what? So basically you would, okay, you can imagine them arranged in a few ways. So here's the transmitter, receiver 1, receiver 2. If it's one-dimensional, if receiver 1 will get everything and absorb it, and receiver 2 will get nothing. On the other hand,
if the transmitter is in between 2 receivers, like on the left hand side and on the right hand side, in that case scenario,
right.
I'm talking about.
So the arrivals at the absorbing receivers. So yeah, if the transmitter is between the two receivers,
Yes,
the
sir.
Brownian motions of each molecule are independent. So conditioned on the time of release of every molecule, the arrival times will be conditionally independent. Now, if you don't condition on the transmitter time, then there will be a dependence, and that will depend on the distribution that you apply to the release times. So yeah, and I think I expect that as the receivers get further apart, they would tend to get more independent, but I'd have to think about that a little more. Okay, I hope that was a satisfactory answer. Thank you for the interesting question. Okay, I think we were here. Can we use the techniques of wireless communication to mitigate ISI in molecular communication? Like adding cyclic prefix in OFDM? So the answer is yes. We talked a little bit about that above. So any technique you use in a linear baseband channel, you can use in molecular communication with the caveat that the channel is non-negative. But there are ways, as I mentioned, there are ways to take that into account. Question here, or if we use coding techniques to reduce ISI, how much is it convenient for molecular communication? So I assume this is asking if it's computationally feasible. So anything is computationally feasible if you assume that it is. As far as how actual systems work at the nanoscale, like natural systems, what we actually see a lot of is, for example, a cell will release a lot of a certain chemical, and then the cell will also release sort of like a canceling chemical to wipe out what they sent. So in other words, there's a big concentration pulse, and then there's something that eats that concentration pulse that drives the ISI low. So apparently, nature has actually found that ISI is also inconvenient. In macro scale type systems, you can basically do whatever you want. You can add any kind of processing that you like. We talk a little bit about interference. I think the electron MIMO is coming up, so we talk a little bit about interference there. As the CSK experiences a lot of ISI, if we use some other modulation techniques, like using two different kinds of molecules, will that help to ease off ISI? Yes, I think if we come back to this question, where is it? Come back to this question. What if we send unique signaling molecules every time from the transmitter to avoid the arrangement problems? So the arrangement problems and ISI are basically equivalent problems. So if you send a unique signaling molecule every time, then there's no ISI. You simply wait forever for that molecule to arrive. So it is definitely true that you can mitigate ISI using different kinds of molecules that will basically allow you to transmit information, a little faster by allowing the ISI to decay. So yeah, the answer to that question is yes. That's all the questions that I was provided with, and I would be happy to answer any live questions if we have time.
Thank you, Professor, for answering all the questions. Like, if anyone else has any questions from the participants, they can raise their hand or type in the Q&A box.
Any plans to prepare best readings in molecular communication?
There was one not so long ago. There was a Communication Society best readings. I can again send you the link.
Okay.
It is a little bit out of date. So I could think about some papers. There was also actually, now that I think about it, there was an issue of the proceedings of the IEEE dedicated to nanoscale communication not so long ago, and that has some very nice papers.
You mean IEEE proceedings? Proceedings
Yes.
IEEE, I see.
Yes.
Okay, if there are no other questions, I'll thank Swami and I'll thank Andrew for very interesting lectures. Yeah, thank you all.